Welcome to myprojectbazaar.com.
In this, we are going to discuss about low power dual dynamic node processor hybrid flip-flop featuring efficient embedded logic. Technology and the speed are always moving forward from low scale integrated to large and VLSI and from megahertz to gigahertz. The system requirements are also rising up with this continuous advancing process of technology and speed of operation. In synchronous systems, high speed has been achieved using advanced pipelining techniques. In modern deep pipeline architectures, pushing the speed further up demands a lower pipeline overhead. This overhead is the latency associated with the pipeline elements, such as the flip-flops and latches. In existing work, they possess a hybrid architecture that combines the merits of dynamic and static structure. In addition, SDFF has a distinctive capability of incorporating logic very effectively because unlike the true signal phase latches in your and other experiments, only one transistor is derived by the data input. This greatly helps in reducing the pipeline overhead since the delay and area associated with one or more logic states preceding the flip-flop can be eliminated. Several hybrid flip-flops designs has been proposed in the past decade, all aims at reducing of power, delay and area. Here in recent years, there are several flip-flops introduces a flip-flop architecture named cross-charge control flip-flop which has considerably advantages over SDFF and HLFF in both power and speed. It uses a split dynamic node to reduce the precharging capacitance, which is one of the most important reasons for the large power consumption in most. But this structure still has some drawbacks due to redundant power distribution that results when the data does not switch for more than one cycle. Also, the large hold time requirements makes the design of timing critical systems with XCFF and involved process. Finally, despite having a small data-driven transistor, embedding logic to XCFF is not very efficient due to the susceptibility to charge sharing up the internal dynamic nodes. In this paper, we possess a new dual dynamic node hybrid flip-flop and a novel embedded logic model. Now I am going to discuss about flow diagram of our project. In the first stage, we design the CMOS structure of the T flip-flop structure for initial stage of NAND flip. In this NAND gate, we provide the CMOS structure and after that we extract the HDML structure because of the D flip-flop providing the CMOS architectures of in NAND based architecture with master and slave structures. From that after the constructions of CMOS flip-flop, it provides the cascaded arrangements of D flip-flop for 4-bit ripple down counter. In this structure, here we can view the circuit diagrams of our proposed architecture. In the first stage, this gives the CMOS structures of overall D flip-flop. Here, the P-type and N-type combinations will describe the circuit connections for to providing the D flip-flop arrangement. The inverters will use the clock cycles for each and every gates and the output will use the Q and Q bar outputs for D flip-flop arrangement. Now I am going to explain the running procedure of our project. In the first stage, we create the architecture designs of CMOS for our proposed D flip-flop design. This is our overall architecture designs of CMOS design for our proposed CMOS design. Now I explain the running procedure of our project. Now select Setup Simulation option. In the general option, add the library files. Now click the transient or Fourier analysis, and in the stop time and maximum time step, here choose the stop time limitations and maximum time step limitation. Here I choose 100 nanoseconds and 10 nanoseconds. Now click OK. After the setting of simulations, now export the file. Now select export and export SPICE. Here it will export the SPICE file for our proposed CMOS design. After that, select Start Simulation button. This will simulate the overall architecture design of our proposed design. After selecting the simulation button, this will generate the SPICE netlist to codings. In this coding, this will display the NMOS and PMOS elements of our deep flip-flop architecture. Here the last lines displays the inputs and output pin details, that is VDD, V clock pins, and the output waveform structures. We can view the waveform structures by click the Run Simulation button. This will check the internal structures of each and every lines in the netlist file and generate the errors and warnings if there was present, else it will display the waveform structures for our proposed architecture. In the WEdit window, this will display the waveforms of our proposed design. Here this will be displayed as a combinations of waveforms. We can view as a separate by clicking Expand Sorts. In the first line, this displays the clock input, and the second displays the data input, and third displays the outputs Q. In the first, each and every clock of negative clock periods, the data input not present in the Q outputs. At each and every positive clock edges, the data input will be present at the Q output as represented in truth table of normal D flip-flop architecture. This is our waveform structures of our proposed D flip-flop arrangements of CMOS design. Now I am going to explain the running procedure for 4-bit down counter for our proposed D flip-flop architecture. This is our 4-bit D flip-flop architecture in a cascaded manner. Now select the Setup Simulation. Here we choose the general option and add the library file. Then select transient or Fourier analysis to choose the stop time and maximum time step for our simulation results. And press OK. Then next, export the file by click the File, Export, and Export SPICE. This is to export the overall circuit architecture to a SPICE netlist file. After exporting this, we select the running option by click the Start Simulation button. This will simulate the total architectures by using SPICE netlist file. After selecting the simulation button, this will generate the SPICE netlist to codings. In this coding, this will display the NMOS and PMOS elements of our deep flip-flop architecture. Here the last lines displays the inputs and output pin details, that is VDD, V clock pins, and the output waveform structures. We can view the waveform structures by click the Run Simulation button. This will check the internal structures of each and every lines in the netlist file and generate the errors and warnings if there was present, else it will display the waveform structures for our proposed architecture. In the WEdit window, this will display the waveforms of our proposed design. Here this will be displayed as a combinations of waveforms. We can view as a separate by clicking Expand Sorts. In the first line, this displays the clock input, and the second displays the data input, and third displays the outputs Q. In the first, each and every clock of negative clock periods, the data input not present in the Q outputs. At each and every positive clock cases, the data input will be presented at the Q output as represented in truth table of normal D flip-flop architecture. This is our waveform structures of our proposed D flip-flop arrangements of CMOS design.